Sure, let's start. So this presentation is about desktop application testing framework that we called Star Recon Exploit. My name is Santiago Gimenez Ocano. I'm a staff security engineer at Praetorian. I've been at Praetorian for more than 4 years and done more than 65 security engagements, and mostly I focus on product security. I have a master's in computer science, a number of certifications, and I'd like to contribute to the community by participating in DC 45 up in Logan, Utah, and the SaintCon's Hacker Challenge.
Hello, everyone. I'm Ryan. I'm also a security engineer at Praetorian. I'm a reverse engineering enthusiast and cryptography enthusiast. I also do more of the product security type engagements, web, mobile, desktop. As far as education goes, bachelor's in computer science, bachelor's in math. I own alphabet soup of certifications. As far as community stuff goes, I'm a volunteer red teamer for the Midwest Collegiate Cyber Defense Competition, as well as the Department of Energy Cyber Force Competition.
So the goal for this presentation is to talk about the differences between a desktop security assessment versus a web and mobile one, and then introduce this systemic approach for desktop application security assessment. The approach will involve 3 steps: threat modeling, enumeration, and exploitation, and we will cover the fundamentals of for Windows, macOS, and Linux platforms. Hopefully at the end of this presentation, you will have actionable knowledge to identify and assess critical vulnerabilities in desktop applications. So before we dive into the framework, let's do a quick introduction. What is a desktop application? It's a piece of software that is compiled and run on Windows, macOS, or Linux platforms. They are normally executed by a local user and might not or might have exposed ports to the internet. This application might include a UI and CLI with parameter support. Something that is common in web applications is the concept of thick versus thin client. A thick client does all the processing locally and then connects to a backend server versus a thin client that connects to the backend service and then lets the backend do all the processing. If we want to compare the different assessments, web, mobile, and desktop, we can use different aspects. So, for example, when it comes to users, a web application will have multiple users, but we don't consider an operating system user. On a mobile application assessment, we will consider one application user and one OS user. And in a desktop application, there are multiple users with multiple OS users. In terms of resources, web applications run in the cloud. They are ephemeral and consume large resources. Mobile applications only run on one mobile device with limited resources, and desktop applications run on computers with medium resources. In terms of access to those applications, for web, we will only have network access. For mobile and desktop, we will need physical access to the either mobile device or the computer to access the application. Finally, in terms of OS integrity, we consider that the web operating system and the mobile are guarantee integrity, and the desktop application does not guarantee integrity. In terms of architecture, we have, for web, we have multiple services or a monolithic application approach. In mobile, we will have a monolithic approach, and for desktop, we can have multiple applications running in parallel or a single application. So now let's dive in a little bit on this testing framework. As we said, we will use 3 steps: start, recon, exploit. In the first step, we will do some threat modeling. In the second one, we will do application enumeration. And in the last one, we will do vulnerability exploitation. So let's start with start. Let's do threat modeling. There are multiple ways to do threat modeling. Here we present a very simple approach with 4 steps. Identifying the attack surface, the user roles and threat actors, the critical assets, and the attacker goals. The attack surface are all the components and features that are directly accessible by an attacker. The user roles and threat actors are all the security relevant privileges that an attacker can assume. The critical assets are the essential components, considering the business risks. And then the attacker goals is what an attacker wants to do with each of those critical assets. So if we consider an example of a desktop application used by a hospital that has 2 roles, and that stores data locally in a database that then is migrated or synchronized with a database in the backend. We can focus on a desktop application that has two privileges that stores a local copy of that database with sensitive information, and that synchronization in the backend. If we want to make a diagram of that application, we can see a simple application with a local database running on a local machine. We can see how the application connects to the backend. And then we can see the application user interacting with the desktop application, and we see the local user interacting with the local machine. For our threat modeling, our attack surface will be files, library, and drivers, that internal communication between the application and the database, and the communication between the application and the backend. If we consider roles, we will see that we have a couple of authenticated users, but also we can see that there might be a local attacker and a network attacker. For critical assets, all confidential information, if we think about the hospital application, all the patient's data, all the administrative data is confidential information, and also the hardware resources. So what the attacker wants to do, well, their goals are very simple. Either abuse the UI, the local database, or that communication to access that confidential information, or abuse the UI to control those hardware resources. If we rethink our diagram, we can see that now we have a malicious application user interacting with the desktop application. We have a local attacker interacting with the local machine, and we have a network attacker interacting with the communication between the application and the backend.
Cool. Yeah, and so once we've actually spent time going through our threat model and understanding what it is the application is supposed to be doing, we go into the recon step, where we're really focused on enumerating all aspects of the attack surface that would tell us what vulnerabilities make sense to do and what vulnerabilities don't make sense that exist. And we can really break down all the techniques that we're going to use here into two main categories: dynamic testing and static testing. Dynamic testing involves when we're running the application and observing what behavior it's doing, right? So some of your first thoughts might be, oh, you're going to run it through a debugger and check it out step by step. True, but there's also other things we can check. Network traffic analysis is super important in modern applications. So is looking at memory for what secrets might be in there, as well as some injection testing, as well as examining the file system. As for static testing, that's when we're going to be examining what it is we actually have on disk. So while we might see certain activities with dynamic testing, it's only when we go in and actually try and do some static reverse engineering or source code review that we might find hidden functionality that wasn't immediately obvious. This step will also involve some sort of dependency analysis and binary analysis as well. Starting on the dynamic side, for network traffic analysis, we're going to be looking at what traffic is happening internally and externally. In the example we have above, we have a demo app called Patient Data Downloader that when we go to fetch patient data, it's going to go and make a HTTP request to a server and pull down that patient data.zip. Obviously, oversimplification on how things actually work, but from this we see that we're using clear text HTTP traffic, which will come into play later. We can use netstat to evaluate open ports and active connections, as well as using TCP dump or Wireshark to view those packets in transit. Now, these days, I'll be honest, I don't think I've seen a desktop application that doesn't make some kind of external connection. So using a proxy such as Burp, Kato, Zap, you name it, just like web and mobile testing, using a proxy to examine that HTTPS traffic as unencrypted and modifying it, tampering it, seeing what happens with backend APIs and how that might be reflected in your desktop application. Moving right along, we have debuggers and system calls. So on screen here, we have a screenshot from LLDB. It looks a little intimidating, but that's because we're actually looking at the assembly instructions going step by step through the binary. Now, not every application is going to require you to dig into such a low level of code. Certain languages and frameworks will have their own debuggers that would be much easier to use. For instance, the .NET framework with C# using dnspy will essentially reverse engineer and show you that compiled executable as the original source code due to nuances with the programming language. However, on top of just debugging the binary, there's other things we can look at as well. Tracing system calls and file interactions using tools like Process Monitor, strace, or dtrust for their respective operating systems will give us more information as to maybe like what system calls or like functions of the operating system for those who don't know. What system calls are being invoked, what parameters are being passed to them, what file handles are being opened. All of these give us a sense of what things are happening on the system that we can potentially mess with. Speaking of the file system, as we mentioned, should be considered as part of the attack surface for a desktop application, as you know, people will be signing in locally and then using the application. Frequently, we see that desktop applications will use files for local credential storage, such as through such as storing credentials and whatnot. So looking at the file permissions, database access, and encrypted storage validation are all important steps here. Specific abuse cases here kind of depend on the implementation, but what's important here is you take the time to first identify what files are being used by the application, then what is actually in those files, and finally, if there's anything else you can do with it. So the file tool is very useful for that first step, using strings and bin walk and other reverse engineering techniques to understand what those files are, as well as using LSOF to identify, or Process Monitor to identify open files. Suppose an application restricts your access to one part because you don't have the right authorization level. If you can just read that file on disk, that's a bypass. But moving now from more of the dynamic testing to the static testing, we have reverse engineering, right? All code is open source if you're really good at reverse engineering, and that is especially true here. Suppose we don't have access to source code, which is often the case with a lot of bug bounty programs and even black box desktop assessments. So taking the time to open it in Ghidra, IDA, or Radar can give you great insight into what is actually happening behind the scenes and can give you a look at maybe some hidden functionality that you weren't previously aware of. On screen here, you can see that just by opening this app in this demo app in Ghidra, we see a hard-coded license key. Maybe this is something that is included in every distribution of the executable, and we could point that out as being like, hey, if somebody finds this, they could just activate whatever products they want. Again, like the debuggers, we have language and framework-specific versions. So for .NET, we have dnspyx, and for Java, any number of tools these days, JADX, JDGUI, Recaf. All of this in the name of really understanding what it is our application's doing. And whether you've obtained source code through your engagement or you've reverse engineered it, it's important to take time to actually review it. Frequently, what we end up finding here, for one, is hard-coded secrets in the source code, as I mentioned earlier, hard-coded license keys, but other things such as, AWS credentials possibly, or other relevant secrets that could be abused. Using a tool such as Nosy Parker is especially useful in automatically sifting and scanning through maybe hundreds and thousands of lines of code for, secrets using known regular expressions. Additionally, one weird thing that I find in a lot of desktop tests is weak cryptography. For some reason, people are still trying to roll their own crypto. Do not do that. You will not win. You will not succeed. Weak or custom algorithms to store credentials oftentimes can easily be reverse engineered or debugged in such a way that they can get leaked. So it's important to keep an eye out for those. And as with any application test, taking the time to identify your sinks, that is your insecure functions, leading to vulnerabilities such as, buffer overflows, insecure deserialization, database injection, file manipulation, command injection, you name it, right? So using a static analysis tool, a static code analysis tool such as semgrep, CodeQL, to go through and identify that low-hanging fruit can be especially useful to find a place to start. That said, don't rely on these tools to be your sole source of truth for any vulnerabilities, as these tools are known to provide many false positives and false negatives. So manual review can also show you maybe more of the business logic related vulnerabilities. Additionally, worth taking the time to look at vulnerable dependencies. There are automated tools out there like dependency check or depscan, which will take time to identify what libraries might be in use. Many applications end up using dependencies that are maybe a decade old, and while a lot of them don't end up doing that much, you might find one that has a vulnerability in it. And now we move to the exploitation phase that everyone's been waiting for.
So in this section, we will talk about specific desktop vulnerabilities. We want to start the first one talking about injection. Injection is the most important risk in OWASP top 10 desktop from 2021, and it can include a wide number of examples, such as SQL injection, LDAP injection, XML injection, and OS command injections. These type of injections normally depend on the type of programming language and technologies used by the application, and normally there are two ways to test for injection. One is manually by sending special characters and seeing how the application behaves, trying to identify error messages. And the second one is automatically using a technique called fuzzing with tools such as AFL++ or WinAFL. The next vulnerability we want to discuss is unquoted services path. So in Windows, you have the concept of services. They have these that have this property called path to executable. If the value of this path to executable is not enclosed in quotation marks, Windows will break that at spaces and look for executables after those spaces. So for example, if we have the path with program files and security demo with spaces, Windows will attempt to execute program.exe, program files / security.exe, and then the full path. An attacker with access to the system and that can place those executables where Windows is going to search for it can abuse the application and escalate privileges. If you want to find all services with unquoted paths, we just put a little command on the slide. Another interesting approach is library hijacking, which is replacing legitimate libraries with malicious ones. Specifically for Windows, we can see that an application will try to find DLLs in many places. If an attacker can modify those DLLs or can place a DLL in one of those places, the attacker can, again, escalate privileges by having those DLL being executed by the application. If we want to detect this type of vulnerabilities, we can use Process Monitor or Accenture's Spartacus.
Yeah, and then the next class of vulnerabilities we want to talk about is related to IPC. Now, IPC stands for Inter-Process Communication, which essentially describes any functionality where processes are exchanging data or sharing data with each other. Now, with how generic that definition is, of course, the actual exploitation details will depend on what IPC actually is for your application. Some examples include .NET remoting and Java remote method invocation. Both of these are for two different frameworks, but it's essentially the same feature where you can essentially invoke in the current running process some kind of arbitrary code, which ends up being a super juicy target for a lot of testing. Additionally, Unix sockets or named pipes, that is, mechanisms on the operating system that allow you to pass data in and then read from it later. Many applications will assume that the application is the only thing that can send data or read data from those pipes, but if permissions are not properly configured, you might find some way, some unsafe function on the other side of it that you can abuse, or potentially some data leak coming from it. On screen here, we specifically have a rough diagram of the Electron process model. Now, Electron is a framework that allows you to effectively run web apps as desktop applications by packaging that JavaScript into a local executable. And frankly, it works very similar to web itself. I do have a laser pointer, cool. So the renderer process is effectively the browser that the user is going to be interacting with. So you have this browser window and IPC listeners that are ready to send off IPC connections. This, flowing from the Electron IPC, goes to the main process, which is effectively your backend for the application. The main process is going to be responsible for window management, the application lifecycle, but for our purposes, more importantly, native APIs and IPC handlers. Now, what you see on screen is probably a lot of information, but hopefully I'll be able to break it down. Here is a vulnerable code snippet where we're defining a new IPC channel for our application. We define IPC main on new window, so we're creating a new channel called new window, and when it's invoked, it'll pass this the URL parameter into shell.openExternal. Now on Windows specifically, if unfiltered input is allowed to come to this function, you can easily get remote code execution. So, for a second, suppose your application has a cross-site scripting vulnerability. That is, you're able to inject arbitrary JavaScript, right? Not only can you do what you would normally be able to do with a cross-site scripting attack, that is, steal cookies, hijack session, maybe a keylogger, but you can also, if Electron is exposed in the renderer process, which it usually is the case, and this could be a talk on its own, if that is the case, you could use the JavaScript to invoke an arbitrary IPC channel. So in this case, we inject JavaScript. We see that if Electron events send new window, and we use this to open the calculator app on Mac. Now on Mac, of course, this only opens a file, so it'll require some social engineering to actually get true code execution. But on Windows, point this to a remote file share that you maybe have sitting on an EC2. Guess what? Code execution like that. Another sort of fuzzier vulnerability category than some of the other ones we've talked about are machine in the middle or attacker in the middle attacks. This requires the attacker to be able to sniff or modify traffic on the wire, as the name would suggest, which is inherently a bit trickier of a position to sort of assess the risk and impact, but that's why we emphasized threat modeling at the beginning of this talk. So remember that desktop application from earlier, the patient data downloader? We said that it was using clear text HTTP. Bad. Suppose you have an attacker sitting in between the connection of the client and the back-end server. Then they could switch out the response that's received from the server for anything else. Now suppose this application has a zip slip vulnerability, which essentially does not properly check the zip file, so when the zip file is extracted, it will unpack a file somewhere unexpected on disk, effectively giving you arbitrary write. We can replace the zip file that the application expects to receive with our own zip slip payload, and while the application says, error, I can't find the JSON file in the zip folder, guess what? We've already written the file to disk. And on top of that, now suppose that we have a library hijacking vulnerability too, where we see that there's a DLL it looks for but doesn't actually find. If we can write a DLL to disk, guess what? We now go from man in the middle all the way to remote code execution, which is pretty cool if I'd say so myself. But keeping it moving right along, another class of vulnerabilities relates to uninstall scripts or pre-install scripts. So Linux and macOS applications frequently come with their own scripts and application users. In our case, our example is the IT support user that can run this uninstall insecure Mac app script as root. Now you'll notice the script here seems pretty innocuous, just runs an echo command, removes a bunch of stuff with our favorite RM executable. Seems pretty straightforward, can't be hacked. Notice that these are being called as echo pkill and not with absolute paths. That is, instead of /bin/echo, it's just echo, or /bin/rm, it's just rm. If we get code execution as IT support through some other vulnerability, we could create rm in the temp directory and modify our path so that it expects to find executables in temp and then checks every other thing. So when we go back to the script, it'll go to echo and it'll be like, okay, echo's in bin. It'll go to pkill, be like, okay, pkill's in bin. And then it'll go to rm and it'll see rm in the temp directory, but guess what? Rm runs bash, and since we're running it with sudo, that's a root shell. So that now we found a chain to essentially get us to local privilege escalation, just through, something that you would do haphazardly while writing this code.
The last vulnerability we want to talk about is secrets in the registry. This is specific to Windows. A desktop application might store secrets in the registry, and we can see that behavior by using regshot to take registry snapshot. The method to do that is very straightforward. Before installation, after the first run, and after we uninstall the application, we take a snapshot, and then we compare all the different changes. So in conclusion, we talked about what makes a desktop application assessment different than a web and a mobile one. We introduced a systemic approach to desktop application security assessments. It's based on threat modeling and enumeration, and we think that by investing time in these two steps, you can have a very good understanding and clear picture of what risk is on the application. Finally, we cover some vulnerabilities for Windows, macOS, and Linux platforms.